Alright, so today we're going to be talking about logic. First, let's discuss that a proposition is simply a statement, and it's either going to be true or false. So let's think about the proposition P. So we're going to have this lowercase p right here as a way that we denote one proposition. So Jan Smith is a student at Franklin College. That statement is either true or false. Jan Smith is either a student at Franklin College or she is not a student at Franklin College. And then the same with proposition Q. That's another way we're going to denote of a different proposition. Is that the temperature outside is above 32 degrees. So if the temperature outside is above 32 degrees, then this proposition is true. If the temperature outside is not above 32 degrees, then this proposition is false. So what's going to be important to note is these are all going to be statements that are there's no middle ground with them. They're going to be true or they're going to be false. All right, so let's first talk about our first thing, which we're going to talk about disjunctions. So this is the statement P or Q. And then the way that we're going to use this little caret symbol to denote P or Q. So instead of writing out the word or, we're going to do P, this little guy, Q. And then what we're going to do is we're going to construct a truth table. So P, Q, P, or Q. And what we're going to do is that we're going to go through all the available options for the truth values of P and Q and their combinations. So P can be true, true, false, false, true, false, true, false. Notice that this ordering of P and true that we did. For P, we went true, true, false, false. For Q, is true, false, true, false. I want us to keep this ordering because it keeps it a little more systemized. So effectively, all we did by doing this is that all we did was able to go through all of the possible combinations of true and false for P and Q. And that's the reason why we did. There are a total of 4 different ways that P and Q could possibly be true or false. Alright, so now we're going to be doing the more interesting thing is the truth value of the statement P or Q. So if P is true and Q is true, then the statement P or Q is true as well. If P is true and Q is false, then the statement P or Q is true as well. Similarly, if P is false and Q is true, P or Q is going to be true. And then lastly, if P is false and Q is false, then the statement P or Q is going to be false as well. So this is what we know as a truth table. And we're going to be building a lot of these. So what's important to note that when we have a disjunction, the only time that a disjunction is false is when both our parts, this or that, are false as well. So that's the only time we're going to have a false disjunction. Alright, so if we're dealing with or statements, we're going to deal with and statements as well. And statements are conjunctions. So this is when we have P and Q. And the way that we denote it, like using little math symbols, is that we're going to do that upside down care. So this is the way that we denote P and Q. So once again, we are going to build a truth table. So we're going to lay out P, we're going to lay out Q, and then we're going to do P and Q. Alright, so once again, we're going to go through all the combinations of true and false for Q. And the way that I like to systematically do that is that we're going to go true, true, false, false for P, and then alternate for Q, P, true, true, false, true, false. Alright, so let's go through the conjunction, the truth value of this statement. So if P is true and Q is true, then the conjunction P and Q is true as well. Alright, so if we have P is true and Q is false, then the conjunction's false. Same with if P is false and Q is true, the conjunction P and Q is going to be false. And then lastly, if P is false and Q is false, the conjunction P and Q is false as well. So the only time that we're going to have a true conjunction is when both are this and that are true as well. So the only time we hit this and that, the whole statement is true, is when this is true and Q is true. All right. So we've done disjunction statements. Those are the or type of statements. We've done and statements. Now we're going to do if this, then that type statements, or we're going to say conditional statements. So if P, then Q type situations. And then we denote this mathematically or using symbols as P implies Q. Sometimes you'll see them use this little double equal sign. Either way, I like to use the single one just because it's a little bit easier. And I'm lazy. So we're going to build a truth table. P, Q, P implies Q. P is true. P is false. True. P is false. P is false. True. False. True. False. And then we're going to go through the truth value of P implies Q. So if P is true and Q is true, then P implies Q is true. If P is true and Q is false, then the conditional statement, if this, then that is going to be false. Alright, if P is true and if P is false and Q is true, then the conditional statement is true as well. If P is false and Q is false, then the conditional statement is true as well. So these two examples can catch students up a little bit. And what's important to note is that we're starting with a false premise. So we're saying if this, then that. If the original this is false, then it doesn't really matter how Q is. The conditional statement itself is going to be true. And we sometimes call these two vacuously true. If P is false, then the conditional statement P implies Q is going to be true. And sometimes we consider these to be vacuously true. So the only time that we have a false conditional statement is when we have a P implies Q, when P is true and Q is false. So that's the only time we're going to have a false conditional statement. All right. So we can talk about negations. So this is the example of not P. Or the book uses this little symbol. I like to use the little tilde symbol. Either way, what we're saying is not P. So if P is true, then not P is false. If P is false, then not P is true. So let's work with a truth table. We're dealing with P implies not Q. So 1, 2, 3, and I'm going to add in an additional column to account for this not Q thing. So we got P, we have Q. I am adding in this additional thing, not Q, and then we got P implies not Q. So P is true, true, false, false, true, false, true, false. Alright, now it's important to note if Q is true, then not Q is false. So Q is true, not Q is false. If Q is false, then not Q is true, false, true. So we're just going to take the opposite truth value of Q. So now we have P implies not Q. So we're going to be comparing, we're going to be using this column of information with this column of information to be able to determine the truth value of this column. And I got a little messy, so let me erase those guys. Alright, so if we have P implies a false thing, well, let's go back to our original conditional thing. If we have, let's look at the second row right here. That's where we have a true thing implies a false thing, and we can see that is the time where P implies Q is false. So for the very first row of our assigning truth value to the conditional statement, we have a true thing implies a false thing, so that means P implies not Q is false. Alright, let's go to the next one. We have a true thing implying a true thing, so that when we know that this conditional statement is true. And then once again, we have for the last two rows, we can see that we have a false thing implies something. We have a false thing implies a false thing, so that means that it's true. If we have a false thing implying a true thing, then this is another example where we vacuum switch true. So that's how we have constructed a truth table with P implies not Q. Alright. More things that we're going to be looking at. The converse to P implies Q is Q implies P. So we're just going to switch to ordering. The counterpositive to P implies Q is not Q, implies not P. So we're going to, not only are we going to switch to order, and we're going to put a negation in front of both of them. Alright. Then we can say, then we're going to talk about tautology, a contradiction, and a contingency. And basically, if the argument is always true, then we have a tautology. So basically, after we have constructed our truth table, in the very last row, or the very last column, whatever is in this argument right here, if we have truths all the way down, then the entire argument that was emphasized right here is a tautology, because regardless of the truth value of all of our inputs, P or Q, the argument itself is going to be true always. So that's how we call it tautology. Now, let's go on the opposite side of that. If the argument is always false, a contradiction. So if we were to do, we had a final argument right here, whatever it is, and we are getting false all the way down, then we have a contradiction. And so regardless of the truth values of P or Q, we're always going to have an argument that's always false. That's an example of a contradiction. So regardless of the truth value of our statements that we're putting in, we're always going to get a false. So then lastly, if we have some mixture, then we have a contingency. And this is what we're going to get most of the time. So once again, let's compare this last column that we have going on. Let's reconstruct this a little bit. So we have an argument that is at the very last column. And if we just get at least one true and one false in there, then we have a contingency. This is normally what our arguments look like. And we're going to call those ones contingencies. But remember that the final column is always true, we have a tautology. If it's always false, we have a contradiction. If we have at least one true and one false in there, just some mixture of trues and false, then we have a contingency. Alright, so let's go through a couple more examples. So let's go over the example P or Q and Q. So this is what we're going to be kind of doing. We are going to have a combination of these things put together, and then we're going to have to figure out how to construct a truth table for the entire thing. Alright, so we're going to have to construct a truth table. So we have P, we have not, we have Q, and then we have also P or Q. And then we have the entire thing, P or Q and Q. Alright, so P is going to be true, true, false, false. Q is going to be true, false, true, false. Alright, now we have to go through this third column in our table to figure out the truth value of P or true. Remember, the only time, let's go back to our original truth table of a disjunction or an or statement. And the only time we have a false disjunction is when both of our P or Q are both false. So I'm going to scroll all the way back down. So the only time we have a false here is when we have a false P and a false Q. And the rest is going to be true. Alright, so now effectively what we have is a conjunction now. We have, instead of saying P and Q, we have P or Q and Q. And look, we have already constructed the column for P or Q. So now we're going to be comparing this column with this column for dealing with the conjunction aspect of it. And remember, the only time a conjunction is true is when both inputs are true. So if P is true and Q is true, then the conjunction P and Q is true. And look, the rest of the time, if one of our inputs is false, then we know that the conjunction is false. But we're not comparing P and Q, we're comparing P or Q with Q. So we have Q is true and P or Q is true, so that means the conjunction is true. Similarly, if Q is false and P or Q is true, we know our conjunction is going to be false. If Q is true and P or Q is true, then our conjunction's true. And then if Q is false and P or Q is false, then we know our conjunction is false. So we have finished the truth table for this argument right here. All right, let's do one more example. P implies Q and not P implies Q. So we got a little bit of a beefer here. And this is going to take quite a bigger truth table. So we're going to have P, Q. We're going to have P implies Q. We're going to have not P implies Q. And then we're going to have the whole argument. P implies Q and not P implies Q. Alright, so let's fill in our table. We can start with P and Q. True, true, false, false. True, false, true, false. So P implies Q. Remember, the only time that P implies Q is false when we have a true implies a false things. So this one's going to be false. The rest of them are going to be true. With the last two, if a false P, we're going to have a vacuously true statement for P implies Q. Alright, so let's go to this next one. We're talking about not P implies Q. So if we have not P implies Q, that means our not P is going to be false. And if we have a false thing implying anything, we know that this is going to be true. Same with here. Not P is going to, if our original P is true, then not P is going to be false. So if we have a false implies Q, then we know that that conditional statement is going to be true. Alright. Second to last, if we have not P and the original P is false, then we're going to have a true implies true. That's true. And then if we have a not P implies a false thing, then we're going to have a false right here. Alright, now we can put everything together. And basically, when we look at the final argument, P implies Q and not P implies Q, this entire argument is going to be based on this conjunction. So if this is true and this is true, then we know the entire conjunction is true. So we have so when we look at the conjunction, we're going to be comparing these two columns. So if this is true and this is true, then the conjunction is true. If this is false, this is true, then the conjunction is false because one of them is false. If the first one's true and the second one's true, then the conjunction is true because they're both true. And then for the last one, if the first one's true and the second one's false, then the conjunction is false. Remember, when we're dealing with conjunction, the only time the is true is when both of our things are true as well. Alright, so that does it with today's lesson.